My name is Stephen Donnelly. I'm CTO at Endace. We're very proud to be a sponsor of SharkFest again this year. And my talk today is Wireshark at enterprise scale. So we all know that Wireshark is a fantastic tool for looking at packets in a great deal of detail, and it is absolutely used in enterprise organizations today. What I'd like to look at today is what are some of the challenges around the way that enterprises deal with packets and how they deal with the issues of packet capture at scale and how to leverage Wireshark to solve their problems. So I'm going to talk a little bit about why enterprises capture, so why we capture in this case means enterprises, and then a little bit about how capture is done in enterprises and some of the issues that are there, and how we scale, so how you can deal with enterprise issues. So within enterprises, there are lots of different groups who are interested in packet capture for different reasons. And the two main groups, broadly speaking, are the networking people and the security people. And they have quite different perspectives on things, and they have different access to the physical networks and the equipment. There is probably at least one other group, which Steve Ballmer might call developers. And those are people who are maybe developing applications or protocols or even network equipment. Most of their packet capture requirements are fairly small scale, benchtop type work. So they tend to be fairly self-sufficient. But if we're talking about operational use in enterprises, networking and security are the two main groups. So let's have a look at them separately. So first of all, networking teams, first of all, have a huge advantage, and they typically own the network. So they have full access to all of the networking infrastructure. They control the switches, they control the routers and the firewalls, all of the physical infrastructure involved in the networking. And their primary responsibility is the availability and the performance of the networking for all of their users and their services that they're providing. So typically they have a fairly high level view of the network. So they need to understand what's happening in the network at a large, from a high viewpoint, if you like. So they tend to use fairly high level statistics such as SNMP from switches and routers and feed that into a network management system, which can provide them with visualizations of the health of the network at a large scale. If they are looking for a bit more detail, they may collect flow level statistics using NetFlow export or IPFix and put them into flow analysis tools. And there are open source and commercial solutions for that. Generally, they're only interested in doing actual packet capture when they're doing really advanced troubleshooting. So they're trying to understand some very specific problem in the network. It could be performance related. And the only way to solve that problem is to go and get actual packets. So it tends to be a last resort for the networking team. Security team, on the other hand, have in some ways a wider remit. They're kind of responsible for securing the entire enterprise, which is not just the network, but the network is a key part of that. So they're typically interested in continuous monitoring for security reasons of the network. So they're looking to detect intrusions. They're looking for indications of compromise within the network. They may be threat hunting, so they're looking for patterns of activity. They may be scanning for vulnerabilities, either passively, so looking for advertisements of services to make sure they understand the inventory, or they may be doing active vulnerability scanning. They may also be doing pen testing. So when you're doing pen testing and a red team is trying to find vulnerabilities in the network, packet capture can be very useful for blue teams to understand how to defend the network and to understand what the pen testers are doing. Disadvantage for the security team is they often rely on the networking operations team for access to the network. They don't own the network. They may not, depending on the structure of the organization, have direct access to all of the equipment and privileges that they need. So they may rely on network team for access and also for response. So if they determine that changes are needed in their networking, they may actually have to put that through as requests to the networking team. Generally, they are going to need full packet capture in real time at multiple points within the network for deep packet inspection based tools. So the broad categories include signature detection, so intrusion detection systems, which are kind of signature based, and behavioral analysis, so network behavioral anomaly detection type tools. And then finally, they're interested in packet capture and storage, so retaining the packets for evidentiary purposes. So for analyzing incidents after the fact, if there is a breach in the network in your organization, then being able to tell what happened, when it happened, what information was accessed, and so on becomes very critical. Logs from services can be very useful, but if a system is compromised, then the logs can be altered. So having a recording of what happened on the network can provide a independent verification of events. So what can't you do without packets? So what is it that makes packet capture so important, and why do we rely on it in certain circumstances? So from a security point of view, collecting and examining evidence is really key. In order to understand what happened during an incident, you need to see the actual requests and responses on the network and look at what data was actually transferred if you can. Being able to capture packets also helps in developing and testing rules, so signatures, and testing ACLs. So if you're testing firewall rules and so on, then being able to do packet capture, being able to vary the packets and then see what is passing through, it can be very helpful. From the networking point of view, there are certain problems in the network on the transport layer that you can really solve best or only with packets. Being able to see the protocol details and the specific application errors that are being returned is much easier from packet traces, because their individual applications may not be directly accessible. It might be a client device that's external to the organization, for example, and they may not capture the level of detail that's required. And then also a lot of performance issues require packet level information rather than flow level information. So a flow level summary will tell you who is communicating at what time and maybe some bulk statistics, but you need to see the individual packets in order to understand TCP sequence numbers, window sizes, all of those kinds of things. Also the ability to measure latency, so service response times, look at microbursts in the network and so on. And then finally, in some cases, it's fairly limited, there can be regulatory compliance around performing packet capture as well. So particularly in the financial industry, we've started to see in Europe with MiFID II, for example, there can be requirements around recording historical traces with accurate timestamping in order that regulatory bodies can then understand sequences of events. So for example, when there's a flash crash in a market, automated trading. So what are some of the challenges that enterprises have then compared to what we might see day to day? Primarily, the main problem is scale. So enterprise networks are very large, potentially, depending on the scale. They are typically globally distributed, so they're geographically dispersed. They have high-speed links compared to what we might see at home or on our desktop machines. Huge volumes of data are transferred every day. And there's a trade-off between how much history can I record and observe versus the cost of doing that. So there's a real trade-off to be made there. And even if you can solve the scaling problems, which is how do I manage to do capture in this very large and high-speed network, how do I then understand the data that you get out of it? So if you brought a consultant in and you said to this consultant, hey, we've got the bad news, there's a problem in the network and we need you to solve it. The good news is I've collected hundreds of terabytes of packet traces from all over my network. And here's a list of machines that you can SSH into, and you can have a look at those packet traces. They probably wouldn't be very happy, and they probably wouldn't find that very useful. You need some way to be able to visualize what's happening in the network, index all of those captured packets so that you can then search through to find points of interest. So the visualization helps you understand what might be of interest, and then search allows you to then narrow down and find the specific details of interest. You can't look at hundreds of terabytes of packets in Wireshark. So that was a little bit of the motivation. So why is packet capture important to enterprises? Now we'll have a bit of a look at some of the strategies around packet capture and scalability. So I've sort of categorized this into a progression or a spectrum of different capture strategies. And you can think of the left-hand side as being lower investment, but also lower visibility in total. So you have less coverage, but lower equipment costs. And then as you move towards the right, you're adding visibility, and you're adding coverage, and you're adding history. So we'll look at each of those. So first of all, on-demand capture. So when we're looking at that, the image that brings to mind is an IT guy with a laptop in one hand and a patch cable walking around the network, plugging it into things, trying to figure out what's gone wrong with the network. So the good news there is that there's often low to no equipment costs. You can use what you already have to hand. And this works well at a small scale networks and small scale companies or enterprises. You can use open source tool directly. You just grab Wireshark and do some packet capture, and you can use your existing equipment. On the other hand, it can be expensive in terms of time. So if you only have one IT guy in your company, having that person spending a day traipsing around trying to solve a networking problem could be quite expensive, or you may have to bring in your one networking guy or bring in consultants to solve problems for you. It also tends to be very reactive. So it's a temporary measure. You're plugging into a network somewhere, doing some packet capture, stopping, going somewhere else, as in an iterative process to try and solve your issues. And I think most of us probably have a folder somewhere on our machines, which is full of hundreds of cryptically named files. We no longer know where they came from and what they mean. So it's not really doing good baselining. It's not recording any history that we can go back to solve problems later. The next step along the progression is live inspection. So these are tools where we capture packets continuously, but we don't record them to disk. So we're doing live inspection of the packets. Now, because this is continuous 24/7, it usually needs permanent and dedicated equipment. Sometimes it will co-host with other applications, but frequently it is a separate system. And where you put these systems within your network defines what you can actually see in terms of coverage in the network. There's lots of open source and commercial tools that can be used for this kind of inspection. So Suricata and Snort are IDS systems that are signature based. Zeek is a bit more pluggable and a bit more flexible, but essentially is still looking for patterns of behavior, generating logs. And then there are various commercial solutions as well. And there's a whole raft of companies who produce intrusion detection systems, network behavioral anomaly detection, network detection response, and a whole lot of startups who are trying to apply AI to this area to build better models of what is normal behavior and what's unusual behavior. These can be an appliance model where you're buying a physical box, or it can be a software model where you're deploying an application on a server that you are providing. Generally, what these tools are doing is providing a real-time stream of alerts, which are going to SIEM system, and alerting people to items of interest. And those alerts are usually logged as well to provide a historical summary. And as well as the alert, which will say which particular signature caused an alarm, for example, they may log the specific packet that triggered that alert. So you can then look at that packet and verify that the signature is telling you something sensible, that the trigger has fired in a positive sense and it's not a false positive. The next step along in the strategy guide is triggered recording. There are various different names for this, such as smart recording and so on. I'll put that in quotes. And it's usually an add-on to live inspection. So you have some tool which is doing continuous monitoring and inspection of traffic. And then based on some trigger or some criteria, it will then record some of the traffic, a subset. Typically it's a flow. So you, rather than recording a single packet that caused the alert, it will then continue to record the rest of that particular network flow. The good news is that this uses less storage space and requires lower storage performance than continuous capture, which we'll come to next. But the disadvantage of it is that the trigger criteria has to be configured in advance. So I can configure my IDS to record flows which trigger based on certain signatures, but if there's a 0 day, then by definition, I don't have a signature that matches that in advance. So I can't then trigger and record that traffic. Behavioral systems have a chance of detecting a 0 day because they may see an unusual activity and decide to trigger based on the activity rather than based on specific content within the packets. In some cases, there is a pre-trigger visibility capability as well. So what I mean by that is a flow starts, at some point during the flow, a trigger is raised. Some systems can only capture the flow from that point onwards. Other systems will have some buffering of the flow before the trigger point and can capture some of the packets that arrived before the trigger actually occurred. And that depends on the buffer depth for the application, so it is quite variable. So the right-hand side, the large-scale solution, if you like, is continuous recording. So this is a strategy of recording all of the packets on a link to disk. So you're permanently recording and maintaining a rotating set of capture files or capture buffer, depending on the amount of storage that you have. Now you can choose to do filtering up front. You don't necessarily have to capture everything. So you might have certain subnets that are not of interest, certain hosts that you don't need to capture for, but generally speaking, it's 100% of the traffic that you're looking at. And you want to be doing compression ideally in order to maximize your storage. Now, one advantage of that strategy is that there's no risk of missing any traffic of interest. You don't have to define ahead of time what is interesting because you're capturing everything. So you capture everything, and as long as you can find it afterwards, you can look back. The amount of storage capacity that you have will limit how long you can store that data for. So it's rotating buffer, you're capturing it live, it's sitting on disk for a certain amount of time, and it's being deleted so that new data can be captured. And that provides a limit to the amount of time that you have to investigate something. So for example, if I have continuous capture and I store all of my data for a week, then if an incident occurred more than a week ago, then I no longer have the packet data that covers that incident and I can't go back and have a look at it. So the requirements for how much storage time you want will vary depending on exactly what your motivations are. And finally, continuous recording is complementary to live inspection, so it's not a replacement for live inspection. You will typically be doing both, and it may be co-hosted, so it may be a single device or a single server which is both running continuous live inspection and also recording data to disk. So what is some of the technology that allows us to do this, and how do we implement packet capture using these different strategies? So if you think about on-demand capture, as we said, we kind of talked about someone walking around with a laptop. There's a couple of different approaches though. So the most common one is perhaps capturing directly on an endpoint. So this could be a client device, or it could be a server where we're seeing a network problem. But there's a couple of issues here. One of them is networking, so network card or NIC, network interface card offloads. So when you capture on an endpoint, what you're seeing is the interface between the operating system and the device drivers. And that doesn't map one-to-one with the packets that are physically on the wire or on the radio. And that may make it quite difficult to correlate what you're seeing on an endpoint with what you're seeing elsewhere in the network. So for example, transmit and receive offloads will coalesce packets together. So I might see a single 20 or 30 kilobyte packet, whereas on the wire, the networking adapter actually breaks that up. So the packet counts between SNMP on my switch port and the packet counts based on my packet capture don't line up anymore. And I might be wondering, am I seeing packet loss? It can also be more difficult to do TCP sequence analysis because the sequences on the coalesced frames don't match the ones that are being seen at the server, for example. Also, modern NICs tend to have a number of qualities which affect timestamping. So they tend to have multiple queues for different flows, and they tend to coalesce packets together for interrupt purposes. And that can mean that software-based timestamps can actually be out of order and can be off by a significant amount. And then finally, there's kind of the Heisenberg uncertainty principle, which is by inspecting something, by monitoring it, we actually affect it as well. So if I'm performing network packet capture on a system, I'm using CPU on that system, I'm affecting the way that the network stack is operating potentially, and I'm using some IO for my storage, and that can affect the performance of that system, which might be what you're trying to look at. So ideally, you don't want to capture on an endpoint if you can avoid it. Sometimes it's the only way to do it. An alternative is using your switches. So you can use a port mirror setup on a switch or a span port, and then a laptop or a dedicated machine that you can connect in. A lot of laptops these days, Ultrabooks, don't have physical Ethernet ports, but you can use, in many cases, a USB or Thunderbolt adapter. And some of these are available at 10 gigabits or higher, and even have pluggable SFP ports for fiber connections. So if you pair that with a laptop that has an NVMe solid state drive, flash drive, you can get surprisingly high capture performance. Now you're still limited in terms of how much you can retain, but you could easily produce hundreds of gigabytes of capture files, and that's already probably too large to comfortably open in Wireshark, for example. And then finally, there are portable sniffers. So these are sometimes a standalone device, or sometimes they connect to your laptop through Thunderbolt. They may have their own storage, or they might use attached storage for a laptop, and they can do some hardware filtering and statistics generation built in. Okay, so for the live inspection and continuous capture strategies, we tend to have dedicated equipment. So these are usually rack mount servers that are positioned at specific strategic points in the network. And there's a couple of options for how they can acquire packets. So one of them is the port mirror or span port, as we did in the previous section. Disadvantage of this, though, is that for each one interface that you want to monitor on your switch, you need 2 monitoring ports, one for each direction. And this starts to eat up valuable switch ports if you have a number of different inspection tools that you want to connect in a single point. And also, depending on your switch configuration and the architecture, you may have some limits on the number of tools that can look at the same set of traffic within the switch, just because of bandwidth constraints. An alternative to that then is using a passive tap or an active tap. So passive tap is usually a single link, usually monitors a single link bidirectionally and produces 2 outputs. It's completely passive, and so it maintains the timing and the packet order extremely well. You just need to check that you have enough optical link budget to insert that. You're going to cause some signal loss on the main capture path. Active taps tend to regenerate the signal, so they don't have the same optical link issues. And something which is very common in enterprise network packet brokers. So this is a dedicated piece of equipment specifically for monitoring network links. They do usually look a lot like an Ethernet switch. They have lots of ports on them. They can tap multiple links simultaneously. They frequently have their own timestamping engine, so they may connect to GPS or PTP or NTP for time synchronization. They can optionally timestamp each packet as it arrives at the packet broker, and attach a trailer to the packet with information on which port it was received on. I'll leave questions to the end. I think it's probably the easiest way to do it, and hopefully we'll get a chance to have a look at that. Yeah, so another interesting thing that you need to know is which port on the packet broker did a particular packet arrive on. Oops. And so they can put this information into a trailer and then send that information through to the monitoring tools, whatever type of devices they are. And frequently they have the ability to do filtering and truncation, and some of them will have decryption capabilities as well. Now, as well as simply tapping individual links as a tap would, where they can take all of the traffic from one link, they can usually do some programmable steering. So you can use this for a number of cases. One of them is aggregating multiple slow links together and send them to a single tool over a single port. So that allows one tool to see multiple links, and you can tell which port the packets came from by looking at those trailers that were added. It can also support multiple tools looking at the same set of traffic doing duplication. So internally, the packet broker has a huge amount of bandwidth, and it can duplicate traffic, send the same stream of traffic out to multiple different sets of tools. Might be one's doing packet capture and one's doing live inspection. And another use case is load balancing. So if you have a live inspection system, but it has a limited bandwidth that it can process, then you can use multiple instances of that tool and then load balance a higher speed link onto multiple appliances. And if you're capturing recording packet traces to disk, again, you might have bandwidth limits on a per tool basis, or you might have limited storage capacity. And if you want more storage capacity, you can load balance the traffic across multiple captured devices in order to get a longer overall retention time. Okay. So now we mentioned that where you do network monitoring will affect what visibility you have, so what coverage over your network you have. So here's a fairly old-fashioned network diagram. You can tell it's an old-fashioned network diagram because it has a trusted zone in it, and I think that these days zero trust model networking is more standard. Certainly, I think a lot of people probably have a chuckle about the idea of having trusted Wi-Fi. I don't think that's probably a very good idea. But broadly speaking, here, this is a reasonable diagram to start with. Also, telecommuters used to be a little side add-on. These days in COVID, we call that work from home, and that may be your entire staff. So everybody in the enterprise may be telecommuting now, including your CEO who's trying to talk to investors and things like that. And so you need to make sure that they're having a good network experience as well. So where would you monitor within this network? And this is a great vendor diagram because the answer is clearly everywhere, right? The more points that you can monitor within your network, the more coverage you have, the more visibility you have, the more readily you can narrow down where problems are occurring. On the other hand, in this diagram, these are shown as separate monitoring systems, whereas the important point is that the ability to monitor these interfaces. So each one of these links that has an orange line coming off of it is a point where a packet broker can monitor a link and then direct traffic to a consolidated set of tools. Which are the most important points to instrument for monitoring? I would argue that it's aggregation points and it's administrative boundaries. So a typical example is connections to the internet. So it's an aggregation point, which is a high flow of traffic, and it's an administrative boundary between the inside of the network and the outside. So that would be a key point. But don't forget branch offices. So branch offices frequently run in kind of a split tunnel mode. So they'll have a local connection to the internet with their own firewall, and then they'll have some form of internal access to the rest of the enterprise network. So that makes them a potential point of entry. And it's important to make sure that you're not watching the front door, but not watching the back door. So it is important to make sure that you can instrument those points as well. Okay, so now a problem with continuous capture historically has been, it's been considered impractical because of the amount of storage required and the cost of doing that. So how much storage do you actually need? We can work this out just as a function of bandwidth over time. So 1 gigabit link uses up to 125 megabytes per second of bandwidth of storage in order to capture that data. And that's if it's used at 100% utilization. So over an hour, it's 450 gigabytes. Over a day, it's nearly 11 terabytes a day. And over a week, it's 75 terabytes. And that's just the packets. If you have packet broker trailers, if you have indexes, databases, extra metadata, that will be on top of that. But of course, network links are bidirectional. So a 1 gig connection is actually up to 2 gigabits in total. So at 100% utilization, it's 150 terabytes a week per 1 gigabit of network link. When you think about enterprise networks, you realize this could be a real problem. If I have a 10 gigabit link, that's 1.5 petabytes every week if it's used at 100%. The saving grace, however, is utilization factor. Most links are not being used at 100% 24/7. So here's an example. So this is courtesy of REANZ, which is the Research and Education Advanced Network New Zealand. It's a 10 gigabit plus wide area link. It's from Sydney, Australia to New Zealand. And it's essentially like an Internet 2 type connection, if you like. And here's a couple of graphs. The one on the left is over a 24-hour period, and the one on the right is over an entire week. And there's kind of two interesting points here. One of them is that there's an asymmetry in the traffic. So the green traffic is from Australia to New Zealand, and then the blue traffic is from New Zealand going back to Australia. And this shows that there's an asymmetry in the provision of data. So there's a lot of data bulk data is being sent from Australia to New Zealand, and then less data in the opposite direction, which is going to be X, and maybe requests and so on. And so in this example, it's actually 4 to 1. So there's 4 times as much data in one direction. And then secondly, you can see there's a daily pattern. So during the day, when people are active and doing things, traffic is peaking at 3 gigabits on say a 5 or 10 minute average. It will be spiking to 10 gigabits or higher, but on a 5-minute average, it's about 3 gigabits. And then during the night, the slowest, quietest part of the days, it's falling down to a gigabit or less. So if you average it out, the average total bandwidth in both directions is 2.8 gigabits rather than 20 gigabits that you might have gotten by looking at 100% load. So to store 7 days of data for that link, you would actually need about 212 terabytes of disk, not including any indexes. And that could easily be done within a single system today. So modern enterprise hard drives, 10, 16, 18, 20 terabytes in size, put a few of those in a box, you could easily do that. It's quite practical. However, it is still quite a lot of data. So one thing you may want to look at is compressing the data. It makes a lot of sense. Wireshark can open compressed files natively. And it turns out that some network data compresses really well. So things like packet headers compress quite well. Timestamps are sequential after all. Text, so English text compresses very well, about 4 to 1. HTML, JSON, those kinds of things can compress quite well. And the binary compression ratios there can be 2 to 1 or better. Some of the other data that's on the network, though, is incompressible. So a lot of traffic on residential networks is streaming media like Netflix or Spotify and so on. And there is quite a lot of that in enterprises too, video conferencing, for example. So data that's already been compressed doesn't compress well. And you can detect that by looking at file types. If you can see the HTTP requests, for example, or attachment types if it's an email. And there's also encrypted data. So data which is encrypted and you don't have the keys for is essentially looks random on the network. So it's not compressible at all. One approach Endace uses is to look at payload entropy, and that can help us to distinguish what type of traffic something is. And if it's information that's not useful, you can truncate it, keep the packet headers. So you can still do TCP layer analysis and IP analysis, but the content being compressed is less valuable. So what's payload entropy? So payload entropy is a measure of the complexity or the compressibility of some data, and it's measured between 0 and 8, where 0 is very regular and 8 is very random. So if I said, here is a packet with 1,000 zeros in it, the description is very short, it's 1,000 zeros. So the entropy would be low. But if I had a packet that had 1,000 random numbers in it, the only way for me to tell you what the contents of that packet is would be to read out all of those 1,000 numbers. So that would be a very large description, and that's something that's not compressible. And it turns out that you can sort of categorize content into different types. English text has a Shannon entropy of around 4 to 5. JPEG images, although they are compressed, they have enough structure in the file format that they are still somewhat compressible with binary compressors, entropy about 6 to 7. Binary data, again, like executables or zip files, there is still a little bit of structure in there. Whereas encrypted data, the actual contents of an encrypted stream has very high entropy. It's well over 7.5 bits out of 8. So compression and truncation together work really well if you can afford to do that. So incompressible payloads, if the information in there is not useful because you don't have the encryption keys or because it's yet another copy of a Netflix video, then you can simply discard the payload for that. You can truncate it. If you are going to do that, you want to do it relative to where the payload starts. So different packets will have different header lengths depending on whether they're IPv4, IPv6, whether they're tunneled, whether they're fragmented, and so on. So you want to do your truncation based on the beginning of where the payload is. All of the data that is compressible, that's not incompressible, compresses quite well. So if you combine those two techniques, you can get a effective compression ratio of 4 to 1 all the way up to 10 to 1 or even higher. So that 200 terabytes of reans data for a week could fit into as little as 20 to 40 terabytes. Or the other way of looking at it, for the same amount of storage, we could store between 4 to 10 weeks of data in the same 200 terabyte space. That's a good way of dealing with sheer scale in terms of how do we capture things. So encryption and decryption, we touched on a little bit, and we said if you have the keys, you can decrypt it. If you don't have keys, you can't. The old-fashioned SSL, older versions, if you had the private key for a server, then you could decrypt the network sessions for that server. And in fact, if you compromised a server and you gained access to its key, you could go back in time and decrypt any of the previous conversations that it had, provided you captured the packets at the time. So that's kind of deprecated now. And newer versions of TLS use ephemeral keys, a perfect forward secrecy. There are other talks in SharkFest that cover this in a bit more detail. But what it essentially means is there's a one-time key that's used for each conversation that's not stored. So even if you know the server keys, you can't then decrypt that information later. There are a couple of workarounds for that. One of them is logging the session secrets on the client side, so SSL keylog file, supported by a lot of browsers. This does limit the coverage. You're only going to see you're only recording the secrets for particular sessions from a particular client. And that's both a blessing and a curse. So it does limit the coverage in terms of what you can see, but on the other hand, for privacy reasons, sometimes that's a good thing. A couple of other approaches for dealing with encryption, TLS proxies or TLS offloading. So TLS proxy is usually a man-in-the-middle style system. So it's terminating an external TLS session, which then has access to the plain text, and then re-signing the information to connect to the client. So that requires being able to put a trusted CA onto client devices. And then finally, there's crypto offload, which is quite common in server farms. So if you have a large web server farm, your TLS connections to your clients externally may be terminated at your load balancer and offloaded with hardware. And then the connection from the load balancer back to the web server is in plain text. So you can potentially monitor that. And look at those packets. However, if you are monitoring on the inside, you then won't see the TLS exchange on the outside. And sometimes it's the TLS exchanges themselves that you want to be able to see. So there's a trade-off of choosing which point you're going to do monitoring from. So we talked a bit about why enterprises want to capture packets and different strategies for how to go about doing capture from small scale up to larger scale. So how do we address some of those scalability problems? So scale is really about comprehension, as we said. If you've got hundreds of terabytes of PCAP files, it doesn't really help you understand what's happening. First of all, there's the issues with how do you physically manage and maintain a capture over a large network, which is fabrics. There's the importance of capture metadata to describe what's happening. Time synchronization, so you can compare things, visualization and search. So let's have a look at some of those topics briefly. So the idea of a capture fabric is that an enterprise network is very large. It can be globally distributed. You've got multiple data centers and branch offices. You've got staff all around the world. You may have multiple security groups and multiple NOCs. You've got tens to hundreds of thousands of devices potentially, and you may have tens to hundreds of packet brokers and capture devices and monitoring tools located around the world. So capture fabric is a way of managing distributed capture and storage and doing search. And the reason that you want to do this in a distributed way is to avoid data backhaul. So if I have to capture packets everywhere in my network and then move them back to a central point for storage, I'm going to generate even more network traffic than I had originally. And even if you're doing metadata generation, so flow level information, you don't necessarily want to send that all back to a central point, because then as you scale your capture fabric up, you then have to scale your central collection data point up as well. Whereas if your search and your storage scale with the edge, then it scales naturally. It's kind of a scale out approach. So that helps with scalability as well. So as an example, this is an Endace capture fabric diagram, but it's broadly similar regardless of which system you're using. There is a potentially large number of probes, and this could be tens to hundreds, in some cases even thousands of physical devices. You may also have virtual devices for cloud and VM environments. And these can be single devices, or they can be stacks of capture devices where they're aggregating storage capacity. Then you need some sort of management node, which deals with configuring and maintaining all of these systems, dealing with upgrades and so on. And then you have some centralized search head end, if you like. So this is a central point where different groups of people can go, they can log in and be authorized, and then have access to the information that they need. So capture metadata. The packets themselves tell us what happened, and incontrovertible evidence, generally speaking, as long as you know where they came from. So you kind of need to be able to answer questions about who, when, where, why, and how. And I've actually done an entire previous talk on that topic you can look at in the SharkFest retrospectives. In terms of who, when an analyst logs into the system, you need to understand who they are and what level of access they have. You may have multiple tenants, you may have multiple business groups or partners who need to have restricted access to only some parts of the network. You also want to make sure that your timestamps are synchronized across the whole system. And you'll need to record the history of that so you can be confident that at the time that you captured data, the synchronization was correct. You also need to know for all of the packets you've captured, where were they captured? Which link were they on? Were they captured through a packet broker? Which port were they from? You want to keep track of your capture tools and versions, what statistics you have from each point, so what was happening on the link, what was happening on the capture devices, were they under high load, were they dropping packets, or are you confident that you're able to capture all of the packets on the links? And there may be some why questions as well. So you may have non-packet information that you want to record. So ticket IDs. So if you have a ticketing system through support, you may have alerts that are being logged by your continuous inspection systems. You may have comments that are being added by analysts. You need to keep track of all of those things, which becomes a lot more difficult when you have multiple capture points. Now, if you do collect all of that information, if you ever need to share some of these packet traces with vendors or with consultants or so on, you need to be aware of anonymization. So you need to make sure you know where that information is stored, how to find it, so you can anonymize it if you need to. So time synchronization, again, have talked about that more in the past. A good timestamping system with good resolution is sufficient for a single point of capture. It allows you to measure round trip times across the network and also service response times. But if you're capturing at multiple points within a network, you really want them to be synchronized so you can measure one-way delay and latency. You can guarantee that the timestamps will tell you about the ordering of packets and what order events occurred in. It will also help you correlating with logs from your different continuous inspection systems and lining up alerts with the packets that generated them and how they move through the network. And then finally, the financial industry, as we said, can have specific requirements, regulatory requirements around not only capturing all of their activity on the networks, externally and internally, but they also have requirements around the level of synchronization that they have to be able to prove. The visualization, as we said, hundreds of terabytes of packet traces. You can't load those directly into Wireshark. It's too much information. So you need to have some way to visualize what's happening on the network over time, looking at connectivity between different devices, what applications are being used, vision into the specific flows and statistics about the network, about errors, and about the capture system itself. And this visualization is usually based on summary data or indexes that are being calculated by your capture systems, and that those indexes also accelerate searching for data. So here's a generic picture of a dashboard with some visualizations of data over time. Search is very critically important. So how do you find one flow if you have terabytes of packets or hundreds of terabytes of packets? So first of all, you want time indexes. So if you know approximately when an incident occurred, that can help narrow down what data you have to look at. You also want to index your packet traces by the addresses of the devices that are communicating, by flow indexes. So most monitoring tools will be able to provide 5-tuple information, for example. You need the ability to efficiently extract packets based on those information. So it's not enough just to know where they are, but your system needs to allow you to go and retrieve those individual packets and find them for dissection or for download. These indexes can be very large. They might be 10% or 20% of your packet storage size, so they can be quite large. And finally, you want APIs. So as well as a nice dashboard that you can log into to do drill down, you want to be able to have REST integrations, for example, so that your SIEMs can automatically have workflows that will retrieve packets related to events and so on automatically, for example. So this is an example of Box doing centralized search. So there's a few things to have a look at here. I hope this isn't too small to see. At the top left, this is a search across 13 different sources. So there are a single search head looking at packets from multiple devices. There's a filter that's being applied. So we're looking for all traffic to or from a specific IP address. And we have a time range, which is 44 minutes. And this was a 44-minute period that was 7 days ago. So this is data that we've collected at the edge of our network, and we're searching across all of it. So the system tells us that there's about 17 days worth of full packet data available across the network, and that there's 30 days worth of flow metadata available. And it's the flow metadata that's being used to render the conversations views and the traffic breakdowns. So we've found 138 megabytes worth of packets for that particular host. And you can obviously download those as PCAP files and look at them on your desktop, or you can just load them directly into Wireshark. So what this is doing is taking those packets and then on the actual endpoint, running a copy of Wireshark and exporting the display to you. And you might wonder, why would you bother doing that? I have Wireshark on my laptop. Well, first of all, it avoids downloading that 100 megabytes or that gigabytes of data from a remote site, it might be in Tokyo or something, to your local device. And secondly, your local device might not be allowed to have Wireshark installed if it's a corporate device, or it might be a Chromebook or an iPad or something that doesn't have an executable available, or your corporate policy may also disallow you to actually do downloads of packet traces at all. So this is full Wireshark, lets you do all of the things you can normally do in Wireshark, including saving packet traces out if that's allowed, extracting objects, following TCP sessions, doing TCP sequence diagrams and all of those things. So as a conclusion, Wireshark is extremely valuable in enterprise. As a previous keynote described in one of the previous years, Wireshark is like a microscope. So it lets you look at a single drop of water and see all of the little microbes swimming around, huge amount of detail, thousands of protocols, hundreds of thousands of different fields. If you can solve the scaling problems of enterprise, so you can manage to do capture at multiple points at high performance, collect the metadata that you need, index it all, and then have it be searchable, then the combination of Wireshark and enterprise is a perfect thing for solving a huge number of problems. So thanks for coming to the talk.